and I'm very thrilled to have AJ and Chandra here from Turbonomic, who are going to talk about optimizing efficiency in cloud-native AI environments. So give a big warm applause for AJ and Chandra.
Thank you. All right. Hello, everyone. Thank you so much for coming. This conference has been amazing, as always, and I'm really excited to be here to talk to you about optimizing efficiency in cloud-native AI environments. We're going to be going through a bit of an overview of why optimization in this space is important, how you can optimize GPU and AI workloads in on-premise environments, cloud or private cloud environments, public cloud environments, and some of the considerations unique to AI in itself. We're going to talk through what we're able to do today and some of the more advanced capabilities that we're looking at building in the future, and then end with an example of what we've actually done within IBM to optimize our own usage of GPUs in cloud-native AI environments. So to start with, I want Chandra here to talk about all of the amazing things that we're doing at IBM Research, which, you know, if I can just say is one of the best parts of working at IBM is being able to collaborate with IBM Research, which is really cool because they do some very cool things. All right, so Chandra.
Thank you, AJ. So a lot of you may be wondering what's IBM Research, and I just want to give a little bit of an overview of why AJ and others in IBM think it's a wonderful place. So we are about 3,000 scientists and engineers spread over multiple countries, and we work on core things which include hybrid cloud, artificial intelligence, quantum computing, semiconductor platforms, cryptography and security. And then we have some core sciences which are kind of spanning the physical sciences, the mathematical sciences, and computer science, and they kind of get infused into some of the key focus areas. So just to get a little bit of a feel for the types of things we do in AI, we just recently announced the IBM Granite foundation model. It's a large language model which is kind of hitting some of the leaderboards. In quantum computing, we have roadmaps for 1,000 qubit plus quantum computer over the next couple of years. We have deployed and made quantum computers available over the cloud. In semiconductors, there are lots of innovations, too many to name, but including things like the DRAM were invented in the same building that you're kind of seeing here. Some of our recent achievements in this space include 3D chips and 3D transistors. Right, in security and cryptography, we're kind of working on quantum-safe cryptography so that data is still safe when quantum machines are actually available in use. So obviously, some of this work has kind of resulted in Nobel Prizes, including things like superconductivity at high temperature, scanning tunneling microscope, and electron tunneling effect. And just as another anecdote, the LASIK surgery was actually invented in the same building. There were a few IBM researchers who got bored after Thanksgiving, say, brought some turkey to the lab, and they had access to various lasers, so they started playing with that, and then they figured out that they can actually devise very precise cuts, and then eventually that kind of turned out to LASIK surgery, right? So going forward. So as I said, we're kind of spread across many different locations. I work in the one in Yorktown Heights in the top left. And we have centers in Cambridge, Massachusetts, right next to MIT, Almaden, Haifa, and not pictured here are sites that we have in Africa, India, and Brazil, and so on. Right? So our mission is essentially to be the organic growth engine for IBM, and then create what's next in computing. And in essence, we want to make sure that the story of computing cannot be told without IBM Research in the picture. So just to sum it up, we have 4 different platforms that we're working on, foundation models and AI, hybrid cloud multi-computer, semiconductor technology platform, and then the next generation differentiated compute platform that we think will fundamentally change the way we can do some things. Back to you, AJ.
All right. So like I said before, working with IBM Research is super cool. The facilities that Chandra mentioned, I get to go there a decent amount, and I was walking around the other day and I saw an elevator rated for 60,000 tons. So just think about some of the legacy computing that had to go up in those like gigantic things, and pretty cool. All right. So let's start talking about GPU optimization, right? And why is GPU optimization where I'm starting this talk on AI? Because for AI workloads to really operate the way they need, they require what GPUs are uniquely capable to do, which is parallel processing of data. So CPUs, right, which are the traditional processing unit that most workloads leverage, are really good at doing diversified, typically sequential tasks. Whereas for the types of computations that are necessary for AI and machine learning and graphics, you require parallel processing. And so this is really critical when you're thinking about optimization in these types of workloads, because the type of optimization you need to do and the things you need to prioritize are fundamentally different, right? Because with a CPU, you're looking at maximizing the latency, how quickly it can execute on those sequential tasks or the different types of tasks that it has to do. Whereas with a GPU, especially in the context of AI and ML, you need to maximize its ability to do parallel processing, how much it can do in parallel and the throughput that it's able to accomplish while doing that parallel processing. And that requires very careful balancing of not only the allocations of how many GPUs you need to for the workload, how much memory is available there, but also the type of GPU. Like based on the types of computations that you're asking the system to do you need something like a tensor core? And there's a lot of considerations that have to go into this. And one of the things that's really powerful or important to keep in mind here is the demand for these specialized processors is continuing to grow and growing astronomically. The entire market, everything we hear about is AI, AI, and graphics demands on workloads are becoming more prevalent. And the fact is, I know for a fact some of our hyperscaler partners are literally running out of the GPUs in certain regions. So I've talked to customers this week that are grabbing GPU-enabled instances and keeping them on as long as possible because they don't want to give up the GPUs. So you need to figure out, how do you optimize? How do you make the most out of the GPUs you have? Because they're really hard to get, they're really expensive, and then relative to our planet as a whole, they're incredibly energy hungry and carbon intensive to actually operate and run. So you want to be very conscious about how you're using GPUs. So, as always, the first step is looking at the infrastructure. We're going to start with private cloud environments. I'm going to just go through this quickly because there's different considerations that everyone needs to think about in these different types of environments in the context of GPUs. So the first thing with on-premise environments is different hardware can have different types of GPU chips. And if you have a workload that was specifically designed for a specific type of GPU, you need to make sure that it's always running on that type of GPU. So even though you can enable virtualized workloads with a vGPU awareness of essentially a virtualized version of that computing system, you need to make sure that as you move it and place it around the environment, that it's always placed on the hardware that has the appropriate type of GPU, which is a very large consideration if you're trying to increase density in these environments and pack as much as you can onto the physical hardware that you have. The second is, if you're moving things around the environment and trying to increase density, it's not just about GPU, it's about understanding the relationship between GPU, CPU, memory, storage, network connectivity, because you have to be able to effectively serve the GPU with the appropriate amount of data so that it can actually start executing on that parallel processing that I mentioned before. And then the last thing is being able to scale the vGPU allocation for these virtualized workloads, because if you over-allocate the vGPU, then you're essentially blocking out a giant chunk of the physical GPU from other workloads being able to consume it. And that's just at the infrastructure. That's not even the cloud native layer of the application that's actually running on top of it and consuming it. And in public cloud, the considerations are very much the same. You have to look at all of the various GPU metrics, think about these GPU metrics as they relate to each other, as they relate again to the CPU, memory, storage, and network on the instance types that have these types of GPUs. And there's a bunch of different types of levers that you can pull in the cloud to get the right GPU allocation for the workload that you're trying to run, but you have to do so with continuous understanding of what the business outcome you're looking for is. Because, and I'm sure you'll hear me say this probably 3 times as I go through this, because if you've ever heard me talk, it's what I say a lot. IT doesn't exist to save money. IT exists to spend money effectively to deliver on business outcomes. And so the key to optimization is performance. You have to understand the performance expectations and what you're hoping to accomplish with every workload deployed in an environment. And only then can you effectively actually optimize the usage. So if you're going to reduce the amount of GPU cards you have or the amount of memory you've allocated to a GPU. You need to understand what the implications and impact you will have on the actual workload consuming that GPU would be. And again, you have to look at more than just the GPU. You have to understand the memory and CPU and storage and network requirements for the workload as a whole, because that has a huge dependency on your ability to actually leverage the GPU effectively. The CPU has to be able to tell the GPU what to do. It has to be able to, the rest of the components have to be able to get the data to the GPU so it can execute on the task. It has to be able to take the output of the GPU and actually leverage it for other tasks and computations. So for AI in general, right, forget about the infrastructure for a second, you have to think about what is AI optimization. And again, as I said before, it's not just about cost optimization, right? You have to make sure that the workloads that you're building, the AI workloads that you're developing, are first and foremost performant, that they deliver what is needed within the time frame expected for a specific type of user. So for example, if someone goes to our good friends ChatGPT or Granite or anything like that, and they propose a query, they ask a question, and it takes 10 minutes for you to get a return, you're never going to use it again, right? It has to be able to respond within the appropriate amount of time, and it has to do so in a repeatable way. It has to be able to perform consistently. And then, like always, you can't actually optimize for performance or cost if you are not compliant from a security and safety perspective. You have to make sure that every decision that you're making from an optimization perspective is compliant with what your business is required to do, especially in AI that's leveraging a massive amount of data. So the data that you're accessing has to be clean, it has to be safe, it has to be secure, and you have to keep those performance considerations in mind when you finally move on to how do I reduce the overall spend on these GPUs and get the most out of the hardware that I have. And the fact is that you have different opportunities for optimization as you move through the life cycle of building, developing, and running AI workloads. If you're earlier in the process, you can have a much bigger impact on the actual cost of running these AI workloads if you can tune how much resources they're actually using, right? Because if you move into the later stages, you can tune and change how much hardware and infrastructure and how you're scheduling the actual resources to be used, but you can't actually impact how much they're actually using in the first place. So earlier in the process, you have to think very critically about what are we actually trying to accomplish? What application are we building, and what does that application need to do? And then what model is the most appropriate for that specific type of application? How do we tune the model and the data that it's being trained on and doing future inferencing on to be able to accomplish what is needed? But then once that application moves into the production side of its lifecycle, the biggest impact you can have from an optimization standpoint is on making sure that you are effectively scheduling the workload across the GPUs that you have and infrastructure as a whole as effectively as you have, and that the infrastructure is configured as effectively as possible to meet the performance requirements at the lowest possible cost for those workloads. And just to end again on this topic of performance in LLMs, it's not just about is the GPU running and it's not too hot and it's at 100% utilization. Is the actual workload doing what it needs to do from a business perspective? Am I getting back the first token, is the query responding in the time frame that I'm expecting it to? Is it doing so consistently? Is it doing so with the appropriate amount of latency? And when you're trying to optimize even just for inferencing, there are so many different considerations you need to think about of the types of optimization you can do in configuring just the inferencing side of AI workloads, let alone on the training side. So with that, I'm going to let Chandra walk through some of what we are doing today in our thinking about how we can continue to optimize these GPUs for AI workloads. And then again, I'm going to come back at the end and talk to you about what we've actually done with this technology inside of IBM.
Thank you. Yeah, can we go one more? So as AJ mentioned, we're kind of focusing on inferencing because we think that is the one that's going to be kind of hit day in, day out. And there's also a variational demand in it because you don't know which users are coming to use which models, what applications are going to peak at a certain period of time, and so on, right? So what's the broad problem here? So essentially there are we view it as three stages. So there's a lot of requests coming in, a lot of users queuing up, different models. So there is an intelligent queue management stage that's kind of at the front, that's kind of queuing up the various requests that are coming in, looking at the SLOs that people have set up and whether the application is interactive or whether it's a batch mode. And so those inputs kind of get recorded. And then the next stage is continuous, intelligent, proactive optimization. So this is where things like load prediction, demand forecast, performance profiles, knowing like what type of resources any particular AI model needs. You may have a 34 billion parameter model or a 20 billion parameter model. So all of these things require different GPU resources and different memory configurations. So we take all that into account. And as has been said multiple times over yesterday and earlier today, carbon and energy is a critical consideration. And in this case, it's even more important because in some cases, you may be overheating the GPU and the GPU may actually turn off some parts of it, and it can lead to resiliency or performance impacts. So we need to take that into consideration as well. So all of these inputs are taken into account, and then we come up with a auto-scaling recommendation to increase the number of GPUs or decrease the number of GPUs, or in some cases, we're looking at fractional GPUs as well. So that recommendation is then taken into the next phase, where in addition to kind of coming up with the recommendations, you need to figure out where to place each of these workloads. So how many GPUs do you have? Which of these are free? Which of these are going to get free in the next few minutes, right? So you take all that into account and come up with a scheduling algorithm, which is kind of doing some of the placement. And this, as you can imagine, has to be continuously updated because tasks are coming in, going back, and there may be various other things that are happening where things are removed from the queue, things are kind of proactively put back in the queue or reordered to be able to meet the various demands that are placed from the users and the SLOs. So one of the things that's happening is that since GPUs are very expensive, people want to kind of think about using fractions of GPUs, especially for smaller AI models, where you may be able to use, let's say, a fraction or a few compute slices. So in the NVIDIA parlance, you can divide up a GPU into 7 compute segments, and they can be configured as 4 units or 1 unit or 2 units or 3 units, and you can have different configurations, right? So in order to kind of leverage some of these mechanisms, you need to have various pieces of software and drivers installed. So you can query and reconfigure the GPUs. You can kind of slice the GPUs, as I mentioned, in different ways to best meet your needs, and then continuously look at the situation and do things like compaction and move workloads around, so you're getting the maximum utilization for the resources that are arguably the most expensive things on the planet today, right? So if you go to the next one. So some of the use cases that we'll kind of talk about and we're looking at are initial deployment. So you have a bunch of workloads that are coming in. How do you kind of best allocate the GPU resources that you have? The next one is migration or compaction. So as the workloads are running, there may be opportunities for you to rearrange things and get better utilization. And then there are situations where you may say step back and redo the whole assignment because that might be a lot more useful for the optimization, right? So with all these, the objectives are to minimize the number of GPUs so you can kind of either use them for other purposes or rent them out or do other things. And then you also want to kind of maximize the use of all the compute and memory slices that you have. And then the other thing is you want to be as least disruptive as you can by minimizing the cost of moving things around. So if there are 2 ways to do it, you want to choose the option which is least disruptive, right? So go to the next one. So just to kind of give you a little feel for what I'm talking about, in the NVIDIA parlance, as I mentioned before, the 3G, 40 GB, for example, means 3 compute slices and 40 gigabytes of the 80 gigabytes of memory that's kind of there on the GPU itself, right? So in the first case, in the initial deployment, let's assume that there are 2 workloads already running on the 2 GPUs. One is 3G 40, and the other one on GPU 2 is 4G 40 GB. Now, in comes the next workload that has to be placed, which is W1, 3G 40 GB. And in the top here, we're looking at what the vanilla Kubernetes first fit assignment would do. What it would do is it would put the workload 3G, 40GB in the first GPU. And then what happens is when the next workload, W2, comes in, there's no way to kind of place it because there is no slot that has 3 gigabytes and 4G 40 gigabyte space available, right? So that job becomes a pending job, and therefore you're not getting the best bang for the buck. Now, if you kind of look at the bottom and look at a more sophisticated algorithm, what it does is it allocates things a little differently. And so instead of kind of placing the 3G, 40GB in the first fit, it's going to kind of place it in the GPU 2. And that's going to allow, for example, when the next workload comes, to be able to kind of place the 4G, 40GB in the GPU 2. So if you kind of look at it in the bottom, you've kind of placed all workloads, and you have fully utilized the GPU resources that you have, right? So that's one of the first use cases of initial deployment with new workloads. So the second use case is migration or compaction. So very similar to the previous use case, now you have 3 GPUs where workloads have been running, and then we get a new, in the top, we have 2 compute slices that are kind of wasted, and the utilization is only 62%, right? So if you kind of look at the assignment at the bottom, what you've done is you've kind of moved some of the workloads such as W4 and W5 into the GPU 1, and W6 is now able to be fitted into the GPU 1, and then you have also moved W2, you've kept W2 where it was and W3 where it was, and then you have one empty compute slice, right? So essentially what you've done is you've taken a workload that was deployed on 3 GPUs and have compacted it into 2, so your GPU 3 is available for you to use for other purposes, right? So if you go to the next one. So if you, So the next one is the use case where you kind of have the complete reconfiguration and redeployment, right? So you have the same 3 workloads, 3 GPUs, and they're kind of running these workloads. But what you try to do is you kind of allocate the workloads to 2 new GPUs. So in this particular case, we've kind of moved things around. And in this particular case, you have kind of wasted no compute slice because all the compute slice are used up, right? So if you compare it with the previous attempt, we had 1 compute slice that was wasted. So in this particular case, we kind of went back to the drawing board and said, if we kind of just assign it to 2 new GPUs, 4 and 5 in this case, then we're able to kind of allocate it even more efficiently than in the previous case. Right. So now I showed you these examples with just 2 or 3 GPUs and 4 or 5 workloads, but just imagine the complexity of all this when you have 1,000 GPUs and thousands of workloads with several thousands or tens of thousands of users, right? It's mind-boggling in terms of the complexity, and how you obviously have to kind of have a computer and AI do this for you and use the most sophisticated optimization techniques so you can get the best bang for the buck for your investment, right? So that's what we've been up to, and then I'll hand it back to AJ to talk about how we've kind of realized some of this in practice.
All right, thank you. That's, it's incredibly exciting to see this type of technology, coming out. And again, throughout all this, it's, how do you take into consideration all of the performance metrics and business outcomes you're looking to accomplish from those GPUs while you're doing the types of activities that Chandra went through? And the thing is each of the use cases that he mentioned are incredibly complex and powerful in isolation, but the fact is you want to be doing all of those simultaneously and continuously. You need to make sure that every workload deployed into the environment is placed in the appropriate place. You need to make sure that as new workloads come in, you can redeploy and reconfigure where those other workloads are placed. And then whenever possible, you want to be able to resize or reconfigure the workload configuration so that you can further increase density of these environments, all without negatively impacting the business outcomes, performance expectations of these workloads. That's really the key to maximizing the utilization of the GPUs that you have, so keeping your GPU and AI costs as low as possible while still delivering on the innovation and business outcomes that your organization expects. So IBM has an environment behind Watson X. I'm sure all of you who are familiar with IBM has heard the term Watson X a lot. We've been screaming it from the mountaintops for a while because we're very proud of all the capabilities that we have there. But behind the Watson X AI and various Watson X environments, there's this environment called the big AI environment, what we call BAM. And this is the environment where IBM does its experimentation, its training, where research does a lot of its work. And before we started working on this initiative for GPU optimization, it was a very manual process. It was exactly what Chandra warned against, which is humans sitting there trying to watch all the metrics and figure out when to do what and how to optimize what. And it led to a very inefficient architecture. Not to anyone's fault, just because that's the capacity of what humans in isolation can do. So what they had was in this one section of this environment, they had a completely dedicated architecture. They had GPUs dedicated to the specific models and specific workloads in those parts of the environment. And at any given point in time, they only ever actually had 3 free A100s. And this made it a problem for the environment because they wanted to load additional models into the environment. They wanted to do additional work in new innovation, new research, and they had to wait for those GPU resources to free up. So it was a very sequential, laborious process to figure out how do you get the performance out of the environment. So we started down this road, and we first built the mechanisms inside of Turbonomic to collect all of this data and get it into the engine so that we can execute on the types of optimization decisions that we've been talking about. So the first is you need to understand the infrastructure. In this case, these workloads are deployed on Kubernetes, and there's implications below the Kubernetes layer and the infrastructure below it, but a lot of that is exposed through the Kubernetes platform itself, and you can understand the cluster namespace configurations, requests, limits, quotas, everything else that you have to understand in Kubernetes. Layered on top of that are the actual GPU metrics themselves, which in this case, we're for now getting them through Prometheus, but we can get them through any mechanism that is able to capture the GPU data that the system requires for the optimization. The most common mechanism is using the NVIDIA DCGM component for NVIDIA GPUs. And then the final thing, because as again, the outcome of optimization should always be to deliver on business outcomes and business objectives, we are pulling data from the LLM service or server itself to understand those LLM metrics, such as how long it's taking it to accomplish what it needs to for each query, what the queue time is, what the querying time is, and we are able to use that to inform our model on how to place and scale these workloads to most effectively use the GPUs. So I know this chart's a little tough to read on this screen, but essentially the red box is before turbo autoscaling was enabled, and you can see there's a lot of variability in queue time and response time, the latency, the performance of these workloads. And at the top, even though it looks like a small dip, it's a very meaningful dip in the number of replicas that are being deployed in this environment to support the workloads. So Turbonomic, with automation, was able to decrease the overall number of replicas that were required to support the outcomes that we were looking for from these AI workloads, without negatively impacting the performance of the AI workloads themselves. In fact, actually improving it to give it a more consistent performant outcome. And as a result, I guess that word should say after. So it doesn't, I don't know what it says before. But after, what we've managed to accomplish is we've taken them from a completely dedicated GPU architecture to an undedicated model where they're able to freely allocate GPUs as needed to the workloads coming into the environment. They have managed to load, I think, at least 10 additional models into this one environment, and we are maintaining a consistent headroom in this environment of 10 free GPUs up from 3. So they're doing more work with fewer GPUs. And this is just the beginning. A lot of what Chandra talked through with MIGs and sub-partitioning of GPUs, like that isn't even out yet, and we're still working on that, but that will take this all to the next level and allow us to compact and get even more and better performance out of these environments. Because I think we can all agree that in this market, we're really just starting. There's a lot of runway in front of us for not only how do we optimize the AI workloads that exist today, but whatever workloads are going to come out in the future and how this is going to progress and the availability of these chips, the carbon impact of these chips, And we really want to work with as many customers as possible and as many users as possible to figure out how do we advance this technology, because that's really what matters, is how do we have the biggest impact possible on the market here. All right, so Chandra, do you have anything?
Yeah, just a couple of things, meaning in addition to the diversity of applications that's kind of constantly kind of increasing, every day we're kind of hearing newer applications for these technologies and newer ways in which these are being used with agentic systems and things like that. There's diversity at other levels, including hardware. Right now, NVIDIA is the leader of the pack, but there's several others like AMD and Intel and others pursuing GPUs in the same areas. So we're going to see a lot more diversity in terms of the types of resources that you can have access to, and you need to manage and exploit, right? So we're really excited about that. And then do you want to talk about the Watson X?
Oh, yes, that's a great point. So actually, we've progressed now from BAM, the environment behind Watson X, to Watson X itself. So anywhere that any of you are consuming anything that's Watson X related, Turbonomic is there in the background in full automation, supporting the actual performance and GPU allocation in these environments. It's been a long journey. They've followed the same maturity path as all of our customers, which is, initial skepticism of a system that automatically reconfigures things, to slowly analyzing, proving to themselves that an optimization is safe, trying it out, learning to trust it, and then eventually flipping the switch and turning on automation so it can continuously deliver as much performance as possible at the lowest possible cost. So I think Watson X is now available in 4 global data centers that are all being optimized by Turbonomic. All right, and so, last thing I'll say before we open it up for questions is, obviously we have not 1 now, but 2 booths here, because we now have our friends in Apptio. So if you either want to come to the Apptio booth or the IBM booth, please come by, and we'd love to talk to you about these use cases. We can even give you a demo, schedule time for deeper demos. And as always, from the product team, I want to hear what you need. I want to hear what we can do more beyond this to improve the offering that we're delivering. All right, so with that, thank you so much, and I would like to open it up to the room for any questions.
Has anybody got a question for the folks from Turbonomic? I think I saw a hand first. Can you catch it, or? No, yeah, you have to speak to it because it's recorded.
Any downtime with the autoscale?
Is there a downtime with the autoscaling? The autoscaling that we are doing, so the rescheduling of workloads across nodes to increase the density and the scaling of replicas, there's no downtime as relates to that. But if you want to go into deeper reconfiguration, there could be some disruption to the workload. It depends on where it is in the life cycle of the workload. But for the most part, in Kubernetes environments, that's why their leverage for this type of technology is they're able to be non-disruptively horizontally scaled, and in between tasks, they're able to be rescheduled effectively onto other workloads without disruptive to the overall application. Chandra, anything you'd like to add?
No, meaning it depends on how you kind of structured the overall models and the computation. So if, as AJ mentioned, in some of the examples I had with the MIG and the partitioning, with some of the recompaction and so on, there could be, meaning you're stopping a workload and moving it to another GPU. So in those instances, you would kind of see some delay. But in the other use cases, now it's a lot more faster. Yeah.
I had a question. So is this technology available for anyone using Kubernetes, or is it restricted to your products?
So the methodologies that we described and the strategy and approach, we are happy to expose to anyone and everyone. We want everyone to advance their use of this technology as much as possible. We have productized and are continuing to productize it inside of Turbonomic itself, which is an optimization engine that can be applied on top of Kubernetes. So no, but there's nothing secret other than the internals of how the Turbonomic engine itself works. The strategies and methodologies are publicly available.
So in one of the slides, you were showing how the first fit approach would fail to allocate all the workloads, and then you had a more optimal placement.
Yeah.
Is that a special algorithm? It looked kind of like it was a greedy algorithm, or I'm sure there's more to that.
Yeah, meaning it's an algorithm we've developed, but it is a fairly standard application of bin packing and optimization technologies. Yeah. But applied in a current context of GPUs and partitions and so on, respecting some of the constraints that these GPUs place in terms of where a workload can be placed. So it's almost like you have a set of bookshelves, but there are restrictions on where you can place a book based on its thickness or its width and size. And so that's how we look at it.
And Kubernetes as a scheduling engine is prioritizing specific aspects of the deployment. Do I have enough replicas? Is the deployment configured the way I need it to be configured? And is it as available and accessible as it needs to be? It's not necessarily looking for optimization on the dimensions of the business outcomes tied to those specific workloads.
Right.
So it's only looking at things from the deployment layer.
Kind of building on the last question about publication, if you were to publish the Turbonomic engine, would that come in the form of like a scheduling and compaction, like a scheduling algorithm that you can apply to the Kubernetes cluster, or a compaction controller, something like that?
So Turbonomic, we have a long history optimizing Kubernetes environments. We don't replace the Kubernetes scheduler. You can kind of think of us as a rescheduler or an optimization engine that gets applied on top of Kubernetes. So we leverage the publicly available exposed mechanisms and levers that Kubernetes has for making sure workloads running those environments are as optimized as possible in every dimension of configuration, vertical, horizontal, as well as all of the various aspects of the deployment, such as limit and quotas and other things. So does that answer your question? Yes. Okay, cool.
Okay.
Look here. So one of the mystery or challenge is to commit the provisioned throughputs in the larger language model. So the question is that a separate consideration or is that interface with the GPU optimization? How do you think about it?
So is the question that, are we considering the throughput of the LLM workload itself?
Yeah, the throughput commitment to have its own kind of satisfaction on the performance, which workloads go first to use those commitments first. Then at the same time, you try to optimize your GPU. Is those two can manage separately, or do you think they will interfere with each other?
So it's continuous evolution. We're right now within an individual workload, we are optimizing it for the throughput and performance expectations of that individual workload. Chandra, tell me if I'm wrong here, but as far as I know, today we are not looking at the higher order relationships and priority between the various models to sort of say, this one is a higher priority model than this one, so this one needs to complete first before that one, if I understand your question correctly. But that is absolutely something that we're looking into, and what we want to do is maximize the performance delivered from the environment as a whole. And I actually think that as we advance in this technology, that's this big space for investment that could be really powerful, which is what are the performance expectations of each individual workload as they relate to each other. And that could have a big impact on what hardware do you schedule each workload on. If something needs to complete faster, I should put it on the faster, newer GPU. Something can be a little slower, I can put it on an older GPU, or even a CPU maybe, if it can be really slow and I don't care how long it takes it to actually complete. That's definitely within the realm of considerations that we're looking at.
Hi. Excellent overview, by the way. I just have three questions. One of them is, how do you determine what kind of, based on a workload, what is the best processor type, maybe even on a CPU, to place it on? Yeah. Secondly, how do you determine the value for the customers? Is there a price calculator, and how do you charge for this?
So what we've done is we've kind of profiled various models, right, on various GPU types and sub-GPU configurations to figure out for a particular load, for a particular SLO, or various metrics like the time for the first token or the total throughput or things like that, and have created that matrix, if you will, of this model for these kind of constraints. What is the best GPU configuration? So it could be a whole GPU, it could be half a GPU, and then we're kind of using that when we're seeing the real workloads and seeing
but
the
the
demand.
application has to specify, it has to come through the request of what type of
So
process?
some of these things are kind of specified in the queuing and various other layers, so we're kind of able to pull all that into the optimization engine, and as I mentioned in one of the earlier charts. Yeah.
And is there a value calculator to show the savings? Like, how do you then charge for it?
Well, right now we don't have a value calculator built, but it's kind of implicit in kind of figuring out what is the best configuration to choose and not overuse or overutilize a CPU or underutilize the resources.
And from a broader Turbonomic perspective, we will capture the impact as it relates to the overall cloud cost or infrastructure utilization. And there's a lot that is even below all this work in the core Turbonomic engine itself to compare the utilization relationship between all the various metrics in the infrastructure as it relates to the applications, as it relates to the workloads, which does help us do things such as pick the appropriate CPU processor, storage configuration, storage requirements for any particular workload broadly, whereas we're just applying that same technology in a more specific, intentional way for these GPU and AI workloads.
Thank you.
Any more questions? No, thank you. Then I'll invite you to the booths of Turbonomics and IBM. Thank you so much, AJ and Chandra.
Yeah, thank you so much.
Thanks for watching. Check out more FinOps X 2024 content on our YouTube channel on the 2024 playlist. Support our channel by liking, subscribing, clicking the notification bell, and by leaving comments and questions for our speakers. We appreciate your support.